Ladies and gentlemen, Mr. is back, and today I am going to talk about the setup. This is the blower mopping. First, why do we need this? Because we are going to make a burner and we need to provide it air, enough air for the combustion, clean combustion of either veggie oil, motor oil, diesel, maybe heating oil later on, and we are going to provide the air from with that. We have a compressor that provides us atomizing air via this little screw that I can thread here. I mean, God damn it. Yes, it will be used to house a Nemo stepper that will sit here, and basically it will be have like a clutch thingy in the middle, and then it will basically be able to step it. And I will put some pressure sensors on it, so it will be basically able to detect how the pressure changes and adjust the pressure, atomizing pressure. But with that, also the amount of air that comes out the door valve. So we need the blower for us to be able to provide around 80, so 80% or 80% of the total burning air. The 20% is provided by the atomizing. Um, Basically, the compressor air is going to be the 20%, and we need all that. But I have already done the what is that? The pump mopping, which means that we have an equation, which I have no clue about how it looks like now. I will maybe have it on screen or whatever. We have the pump equation, so we know if I set the PWM, which we will talk about a bit later. If I set the PWM, which is basically duty cycle, so if I say 50% duty or 50% PWM, that means that the blower or the pump or whatever electronic devices, because these are DC motors, are 50% on, meaning that they operate on 50% RPM, because the voltage, we adjust with the PWM, we adjust the voltage, and the voltage is roughly linear to the RPM, which will result in a linear air carriage and a linear fuel carriage, roughly, and quadratic, so linear fuel and linear air and quadratic pressure on the blower. So catching my thoughts here, we are not just going to run it manually and say, yeah, I have like I don't know, I had this 12 volt buck converter which provided the electricity for the previous blower, which is there, but it was not good because when I started it, it was too much of air, and it basically there is like a screw here that I can adjust the like a potmeter that I can adjust the voltage and the amperage as well. Problem was that it always blew out the fire. So for that, and the second thing is that you cannot not basically rely on something like a manual drive, because you have to adjust the gas, the pilot gas. You need to adjust the compressor air screw. You need to adjust also the blower and the fuel. So that's fourth thing. And if we do not account the ignition as well, that's the fifth thing. So we will need to automate it eventually, so might as well do it now, because that's going to make our life easier. And for that we have I had the this one, the ESP32 based Arduino-ish board, which is a good beginner board, but I have decided to step it up one and use this ST board, which is the STM32 R44 or is it FUC F446RE, which is a great beginner board, I guess, and has everything that we need. It has a lot of timers and all that. So just quick explanation what the STM is superior in is that one thing it has not, it doesn't have more flash memory, nor it has like um, better storage. So those are like like lower, so that's okay. 125 kilobytes and 256 kilobytes, so whatever, or 21, 28, whatever. So yeah, those are lower, sure. It cannot run like Wi-Fi or Bluetooth either, so that's okay as well. We can, but we can use like external boards, which sucks, or we can use one of these for that. But the good thing is that these are so much more reliable, so much more stable than these, because these are pretty fragile because of the a lot of behind in the scenes things that they run. They run the what is this, the Wi-Fi and the Bluetooth and all these logics in the behind, in the back scene. Here you can basically configure the whole thing. This is, as they say, bare metal. So they basically do not have anything unless if you especially enable it. Those always run the things in the behind, but in the background, which is going to take down one, computing power, second, reliability, because it can crash and it is more fragile to that, it is more prone to that, as well as like it has not that many configurations and functions as the STM32. So the STM32, why do I not have focus? So the STM, maybe I will zoom in. So the STM32 is a very nice board, this one, because, or I mean, probably all of them, but this one I can talk about. This, basically, you have like a microcontroller here, and you have like an application. I will show you just in a quick second if I run it. CubeMax and CubeID. So basically you have two applications. One is the CubeMax, which you configure the pins. Basically you can see the whole chip and you can define every single thing. You can enable timers, PWMs, analog or digital convert as digital analog digital, whatever you want. And basically that the application will generate you a code that enables all this into the coder. Then in the coder you can go through, you can add in your code, you can enable the variables and these libraries, and voila, you have a working thing, which is a lot better. And this is why industry actually uses, rather than the you basically will never see anything like the STM or the ESP or the Arduino used in like industrial things. They always use like ST's board, STM32s or ST boards. So yeah, quick intro for that. I have already made in previous videos, so if you haven't seen those, I have already made this, which is basically just two rails. They are called bus rails. Basically there is like a 1 millimeter thick copper plate here, which is 10 millimeters or 12 millimeters wide, depending on how accurate I have cut it. And they are held in this, I don't know if I unplug the connector, I can show you. This is the start round, and the other one is the power 24 volts. It's supposed to be, because I ran it when I designed it from 24 volts, but now I have come on. So I have decided to use it because the 24 volt pump has shit itself. So actually I have decided to move to 12 volt 12 volt, and basically omit the 24 to 12 volt and then to 12 volt side, because I have designed this is the 24 volt side, this is the 12 volt side. So I have already designed this. This is just going to quickly say this is a buck converter, or a a chopper board that is basically here to allow us to PWM. These are this one and this one are the same MOSFETs. These are low-level logic MOSFETs, meaning that they can turn on at like pretty low voltages, 1 point something volts, and they fully saturate at like 1 or 2 volts, whatever. That means that we can successfully and pretty efficiently run PWM without them overheating or breaking down. And we send the PWM from the STM32 to the boards. And for now, I have basically wired them all up, but this one, the 12 volt side, has done some bad behavior, and I do not know if it works. For now, we will leave it like so. So I will have to test it with the blower. I will hook these down and hook up the blower to it, so see if it is working or not. The other side is working fine. So what this does is that it basically, with this chopper board, we are able to set the duty percent. And back to the main quest, that we wanted to talk about the blower mapping. The blower mapping is basically a means so that we plot out the points of, maybe I will draw for you, or if I have the MATLAB on, I will run the code and I will show you that. Be right back, just a quick second, because I have some problems here with the code running. I'll change the directory. So I will run the code, and I don't know if I can unplug it. It will be pretty low quality in terms of like yeah, it will be pretty low quality. So whatever. So basically I have enabled the STM32 first. So we enable the STM32. There is this little pressure sensor that the lines are hooked up. I have already talked about that the differential pressure from here to here will be equal to the amount of air that the whole blower can produce, and that is dependent on the PWM, so basically the rotation velocity of the impeller. That we can control that by the speed of the impeller, and that with the what is the the PWM. So this is going to be really low production value, but or quality. But what I will tell you is that I will show you the exact setup, because I don't want to change the what is this, the V2 PC. So we can see here raw and smoothed. So the main thing is that I have measured the readings of the pressure sensor on empty. So basically I have hooked it up to nothing. It was just 22 atmosphere. This is to show us the baseline of deviation, that there is like this ripple because of the just random noise. And we have been able to identify that there is no pattern or no shift trend. Basically that is because there is like an effect called drift, meaning that over time it goes up or it goes down or whatever it does, but it was not visible here, so we decided that we are going to just average it out, and then that's it, because this is just white noise. So we have identified the middle which is averaged out or medianed out, I do not remember correctly. And then this was the baseline. This was set at yes, it was median at 0.036 kilopascals, and I have tested a few things here basically, so that I turned it on to 20%, then to 40, then to 60, and it was like so, and it was very jumpy. So this was not too successful. I have tried a few things here, but then I actually did the testing. I have implemented a new code, which I might be able to put into the description. I have basically set it so that it starts, it runs for 10 seconds, it doesn't count those values, because there is like initial, how do you say this, ripple and transient. So for the 10 seconds it doesn't log, then for 30 seconds it does log, and then it's going to average out, log the highest, lowest numbers, and it's going to reject some numbers if it is changing quickly. It is called the derivative filter that does that. And basically I was able to log these. I have run 2 tests, and I got this data. I have calculated the Q from the delta P, because I'm going to show you. It's going to be down here. So not this one, this one. So I have written the data in here, which is delta P. This is in kilopascals. So this is 1 bar, this is 100 pascals, this is 176 pascals, or 17 pascals, sorry. So basically this is just a very low 17 pascals. That's like I think 17, no, I think 1.7 millimeters of water, whatever. So I have changed it to water millimeters, which is, yes, 1.7, 1.8, 2.86, and this is roughly correlative to I have already made a empirical equation, which was actually derived from the actual size and ratio of the orifice plate that I use, and that was 2.36 times square delta H. If you have something like this, you will have to probably come up with an empirical calculation, but there is like a standard how do you call this, formula for that that you can use if you don't have this. And basically I have been able to calculate out the Q1 and Q2, and then I have plotted them out versus PWM, which is the duty cycle. So pressure versus PWM, as we can see, it is pretty linear, or no, sorry, the Q is pretty linear. The pressure here is, as you can see, it is starting to curve up. It is going to go exponential, because the pressure is roughly quadratically linear to PWM. So yeah, this is just a fit, so that we derive the equations that basically, how do you say this, represent the data and how the blower behaves. And then we have looked at the residuals, which I actually do not really understand why. This was actually because we want to find if there is like deviance from the main function, and there is a bit of and you want to find some centricity. So basically kind of like this. So it was around 70 and above that it basically did the same thing. So if it is kind of random like this, then it is not that bad. Maybe here and and here. So it was kind of okay. We have came up with the conclusion that it was kind of okay. So then we went with this flow QLS, so liter per second, and we derived this linear fit. And these were the delta P and the Q equations, which were shown here. Is 4.70 blah 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 on the -5th PWM square plus blah 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 blah, and this is this, as you can see. These are the two, and actually we will need to have a inverse these are just the functions, but what we actually want is I'm just thinking now, because we do not want the, yes, I think we want these. We want these PWM and this. Just delete these, and then we were going to write these out, because what we do not have is that we will have the delta or the P and all that kind of stuff. We will need the PWM so that we can know that how much PWM do we have to set it, and the PWM is at this given time is have derived it. Basically, it is this equation here. This equation here for the Q, and this equation here for the or sorry, for the P and the Q. And basically with these you are able to, or I mean I was able to calculate for a 10 liter per second target Q. I was able to do this, and the PWMQ was also set to that. This 0.167 is basically 10 liters per second or ish, and we are able to see that this is 56.776 and 57.0105, which is basically like 0.3.4 ish of 0.34 ish of total PWM deviance between the two, which is very like fine. So about 56.8 ish we would be able to set the target flow to this. And why this is so important is that when we are going to feed forward the fuel, we will kind of know how much fuel we have. And basically, I mean, we will know how much fuel we put in. There might be some deviance from the plotting because of the delta H that the actual system represents, but that's not going to be a big problem, because the with this we will be able to adjust the air so that we somewhat in the neighborhood of 80-85% ish of total accuracy, and then with the rest 15-10% air that will be adjusted with some feedback from a lambda sensor from a car, which is basically there to signal how much air is left in the exhaust gas, and or not air but oxygen. And based on the left out oxygen, we will be able to combust the whole thing pretty nicely and cleanly. So yeah, I think this was it. I think I will upload this. This was not the highest production quality, but what I will say is that still did this video. It is not the best, but this is what you get. Sorry for that. But yeah, I think this is for now. We will tune back, and I will now prep the whole thing. I will make some first. I will make some documents first, so I will not forget this, and I will post this so you can use it and learn from it. And then I will prep everything so that I will be able to hook the I think Mark 0 or Mark 1. I think I will call it Mark 0. So Mark 0 is basically the burner, and it is going to, I mean, it is already made. I have already tested it, but it was pretty shit because I wanted to test it with manually, and it was really just fucking big struggle, I would say, because as I said, 4 things you would have to adjust at the same time, which is actually like doable with or undoable with 2 hands. And yeah, I will now do it because I have automation on my disposal, and or on my in my toolbox, whatever, and that is going to be pretty good and pretty basically easy now that I will not need to do it with hand. Maybe just the pressure compressor air screw, I will have to only adjust that. Yeah, so I think this was it. This was Mace Ringer. Thanks for watching. Do the hard work, especially when you don't feel like it. So, do it. See.